All right, so we are down to our last couple of topics for the semester, and we're going to talk this time about limits at infinity. Um, so, kind of going way, way back to the beginning of the semester, we talked about functions like f of x equals, say, x squared minus 1 over x plus 1, and the limit, say, as x goes to negative 1 of f of x. That is, our function is undefined. For x equals negative 1, but that doesn't mean that the function is doing something crazy when x is close to negative 1. If x is close to negative 1, so negative 1.01, negative 0.995, for instance, our function values, and you can check this out, will be close to negative 2. That is, f of negative 1.01 is almost negative 2. F of negative 0.995 is close to negative 2. And again, you plug those in and see how it goes. We want to take, in this case, f of x to be x squared minus 1 over x plus 1, and we want to find not the limit at, x value like that, negative 2. We want to find the limit as x goes to infinity of f of x. And so rather than x being very close to, something like negative 1, when we want the limit at negative 1, we want to know, how does this function behave when x gets to be arbitrarily large. So we can't say x, is close to infinity. Infinity is not a number. But we could talk about how this function behaves. And when I say behaves, I'm talking about the function value for very, very, very large values of x. And so we're going to look at these kind of from the same perspective that we did our numerical limits back in chapter 1, back at the very beginning of the semester. So let's make a table. And we're going to plug in some very large numbers for x. So this, maybe 10 is pretty big. I don't know, maybe 500 is pretty big. Maybe 10,000 is pretty big. And so f of 10, 10 squared minus 1, divided by 10 squared plus 1 is 99 over 101. And when I plug that into my calculator, I get 0.980198, at least out to, what is that, 6 decimal places. When I plug 500 in for x, f of 500, that is 500 squared minus 1, divided by 500 squared plus 1. I don't know what that is. Is it 24,999 over 25,001 maybe? I'll put a little question mark there. And my calculator out to, what is this, 5 decimal places, 0.99999. And when I plug in 10,000 for x, let me see real quick. Let's see, where's the variable stuff? I get 0.9999998, and then I start running out of decimal places. And so we see that when x is very large, f of x looks to be pretty close to 1. All of these values very, very, very close to 1. And so we will say that the limit as x goes to infinity of f of x is 1. Let's try another one. Here we go. Let's find the limit as x goes to positive infinity of 2x squared plus 3x minus 1 over x squared plus 1. We're changing our numerator up just a little bit. We know that we can use our calculator to help us with this. And if you remember back from the beginning of the semester, we went second and then table settings. Want to make sure we put that independent variable on ask. We'll type our function into, say, y1. And we had 2x squared minus 3x plus 1 divided by x squared plus 1. Yep. And then we can go to second and table. And we'll be able to type in sort of whatever function value, whatever x values we like. So again, we're interested in the limit at infinity, and so we're going to plug in, instead of numbers, say, close to -1 like we did over there in the pink, we're going to plug in very large numbers for x. So maybe 100, maybe 500, maybe 1,000, maybe 10,000. And we notice that all of these values over here on the left side, all of the function values are very close to 2. Now, back when we were looking at limits at the beginning of the semester, we talked about left side limits, we talked about right side limits, plugging in numbers that were to the left of -1, plugging in numbers that were to the right of -1, and we talked about two-sided limits and one-sided limits along the way. Here, with our limit at infinity, we can only approach infinity from one direction, plugging in progressively larger and larger values. There is no coming down to infinity in the same sense that we have left and right-sided limits. However, we can talk about the limit as x goes to negative infinity instead of 2x squared plus 3x minus 1, this time over x squared plus 1. We use the same function that we had just a minute ago, so we don't have to change anything in our calculator. We're just going to plug in numbers that are very large but negative instead. So negative 100, negative 200, negative 1,000, negative 5,000. And we notice this time that our numbers, again, are all very, very close to negative 2. To positive 2. And we're going to say that our limit as x goes to negative infinity is also 2. Now, for a lot of the functions that we're going to work with, these are the same, but these do not have to be equal. They are simply two separate limits, and there's no reason they cannot have two different values. Now we won't get into the calculus of inverse trig functions this semester. That'll be something that we do in the second part. What if we take the limit as x goes to infinity of, this time we're going to do the arctangent of x. And we're going to look at the graph of this one. The graph is going to be essentially the graph of tangent of x, or at least one period of it, turned on its side. And when we talk about, again, these limits at infinity, we're talking about what is happening to the y values on our graph as we go further and further and further to the right. And in this case, those y values are going to get progressively closer and closer to pi over 2. The limit at negative infinity of arctangent of x, as we follow the curve out to the left side, these are going to get closer and closer to negative pi over 2. So again, those left and right side limits, the positive infinite limit and the negative infinite limit, they don't necessarily have to agree. In some cases they will, but this is not a case of does not exist just because these are different, because we're looking at limits on two different sides of the x-axis. So again, these do not have to agree. So that's okay. When we talk about the limit at infinity, when we talk about the limit at negative infinity, for any of these problems, this is called the asymptotic behavior of the function. So, asymptotic, this is one word. Oh, I know it looks like there's a little space in there, but this is really just a single word, asymptotic behavior. It's going to be the behavior at infinity, behavior at negative infinity. So we want to find some. Now these limits, they do not have to exist. Just like our regular limits at finite values of x, these do not have to exist. For instance, if we look at the limit as x goes to infinity of the cosine of x, and we think about what the graph of cosine of x looks like, that's our typical sort of periodic trig function. And this is going to simply bounce back and forth between -1 and 1, no matter how far we move over here to the right side. And so the y values on this curve are never going to approach a single value in the way that they did for our previous limit. Notice that all of these numbers are all very close to 1. If we were to plug in very, very large values for x here, and again, we did that with our calculator, the results were all very, very close to 2. And if you do that with something like the inverse tangent, and on your calculator, this would be written as tangent with the little -1 exponent of x, you would see that these are all very close to 1.57 sort of ballpark. because it's the decimal value for pi over 2. Okay? So as we plug in larger and larger and larger values of x, or more and more and more negative values of x, we're going to start seeing the same decimals kind of show up over and over and over again. That will not be the case here. As we plug in very large values of x, so let's clear this out. We'll put in cosine of x. Make sure we are in radians, which we are, and we'll plug in large values for x. And we notice that none of these are particularly close to any specific value. Now they are all between -1 and 1, but none of them are getting close to a single value, the way that we saw in the table with our previous functions, our previous examples. And so here we'll say that this limit does not exist. And the same kind of thing is going to happen the limit as x goes to -infinity of cosine x does not exist. Now we would like to find these limits using some algebraic techniques. Rather than numeric. For one thing, the numerics can be misleading. If the true limit in our previous case, or our first example, if the true limit was not 1, but say 0.9999999999832, we couldn't tell that from this. Our calculator, our computer, does not give us enough precision with the values that it can show us to distinguish between, a number like that and 1. But we would like to be able to, the calculator is good for giving us a little bit of intuition about it, and a little bit of sort of gut feeling about it, but it's not really, rigorous in terms of the way that the limit is defined. So we need some algebraic techniques to help us out. And we need, along the way, we need a nice little fact. The limit as x goes to infinity of 1 over x to the n power is 0 for any exponent bigger than 0. So as long as we have this 1 over x to some power in the denominator, that limit is going to be 0. And you can sort of check this out. And again, this is not a rigorous proof, but find the limit as x goes to infinity of 1 over x. The limit at infinity of 1 over x squared, or 1 over x cubed, or 1 over the square root of x, or 1 over x to the 3/4 power. Try a couple of different functions and plug in progressively, again, larger and larger values of x, and you will see that all of these limits are going to turn out to be 0. And then a second fact, the limit as x goes to infinity of 1 over x, at negative infinity of 1 over x to the n is going to be 0 as long as 1 over x to the n is defined for negative values of x. Now, what does that mean? The limit as x goes to negative infinity of 1 over x, really is 0. You can graph this 1 over x and look at what happens way out on the left side of it. The limit at negative infinity of 1 over x squared really is 0. I can square negative numbers, no problem. I can do that all day long. But the limit as x goes to negative infinity of 1 over the square root of x does not exist, because this square root of x is not defined when x is negative. So that's what we mean, as long as this 1 over x to the n is defined. And remember, our exponent does not have to be a whole number. We will allow any real number that is positive in our exponent there. This is not always going to be defined, but in the cases where it is, particularly for whole numbers, that limit is going to be 0 as well. And so it is these facts that are going to allow us to put together some algebraic techniques for finding these limits. So let's go back to the limit as x goes to infinity of 2x squared plus 3x minus 1 over, what did I have, x squared plus 1. And we're going to divide each term in the numerator and denominator by the highest power of x in the denominator. So what is the highest power of x that I see in the denominator? It is x squared. And so for this example, we're going to divide everything by x squared. I don't care about the x squared, the numerator. This is the x squared that's telling me what to divide by. So 2x squared minus 3x plus 1 divided by x squared plus 1. We're going to divide every term by x squared. And then we're going to simplify. The replacement theorem says that I am allowed to do this. I'm allowed to simplify functions. I'm allowed to complify functions. So, and complify is sort of the opposite of simplify. I'm allowed to do that even while I am taking this limit. So we have the limit as x goes to infinity of 2x squared over x squared. Those guys are going to cancel. 3x over x squared is going to give us negative 3 over x plus 1 over x squared. All divided by x squared over x squared is 1 plus 1 over x squared. And as long as all of my limits are defined, as long as all of the individual limits are defined, we can find this limit by taking the limit of each term on its own. And I'm going to write this out in all this sort of gory detail this time, but most of the time I won't write it out quite so verbosely. This is going to be the limit as x goes to infinity of 2 minus the limit as x goes to infinity of 3 over x plus the limit as x goes to infinity of 1 over x squared over the limit as x goes to infinity of number 1 plus the limit as x goes to infinity of 1 over x squared again. Again, the limit laws, the fact that the limit behaves very predictably when we apply it to sums and products, sums and differences, products and quotients, composition. Behind the scenes, we're kind of taking advantage of a whole lot of continuity But the limit laws really do allow us to, apply this limit operation to every single term. Now, here we have the limit as x goes to infinity of 3 over x. We're going to use our fact here that says the limit of 1 over x to the n is always going to be 0 as long as my exponent is positive. So that is 0. The limit of 1 over x squared is 0. The limit of 1 over x squared here is 0. And what's going to be left? We have the limit as x goes to infinity of the constant function 2 is just 2, divided by the limit of the constant function 1 is just 1, gives us 2. So we really are taking advantage of the limit laws, where we are applying this limit operation to each term on its own, the numerator and denominator on its own. There really are some very, very powerful things that we can do with limits and the limit laws. And it is this dividing by this highest power of x in the denominator that's making this work. That's what gave us a denominator that turned out to just be 1. So let's try again. Let's try another one. Let's take the limit as x goes to infinity of 3x to the 4th plus 2x cubed minus 5 over x to the 6th plus 4x minus 2. We're going to divide through by the highest, I know how to spell, power of x in the denominator, and that is x to the 6th. We're going to divide every single term in our fraction by x to the 6th. 3x to the 4th plus 2x cubed minus 5, and then x to the 6th plus 4x minus 2. We want to divide by x to the 6th. This step is essentially whatever we do to the numerator of our fraction, we do to the denominator. I can multiply the numerator by 10 if I want to. I can divide the numerator by 1,000 if I want to, as long as I do the same to the denominator. We do this kind of thing all the time when we get common denominators for fractions, when we're trying to add or subtract. So we know that this is a legal and valid operation, and we've got to simplify. 3x to the 4th divided by x to the 6th is going to leave us with 3 over x squared. 2x cubed over x to the 6th is 2 over x cubed minus 5 over x to the 6th. That's our numerator. And then in the denominator, x to the 6th divided by x to the 6th is 1 plus 4 over x to the 5th minus 2 over x to the 6th. And then we will apply the limit to each of our terms individually. Again, I'm going to write this out a few times, but in general, we're not going to write this out every single time. We have the limit at infinity of 3 over x squared plus the limit as x goes to infinity of 2 over x cubed minus the limit at infinity of 5 over x to the 6th over the limit of 1 plus the limit as x goes to infinity of 4 over x to the 5th and minus the limit as x goes to infinity, and finally of 2 over x to the 6th. take the individual limits, and as long as all of them are defined, as long as all of those limits exist, this is a valid operation to do with limits. And then what happens to most of these? The limit of 2 over x to the n is 0. The limit of 5 over x to the n is 0. The limit of 4 over x to the 5th, 0. 0. And that's our fact from the previous page. And then finally here, the limit of 3 over x squared is going to be 0. And what's left behind? 0 plus 0 minus 0 over the limit as x goes to infinity of the constant function 1 is just 1 plus 0 minus 0. That limit is 0. And this may seem like a lot of work to get to this limit, but really behind the scenes, this is what's going on. Again, I'm not going to write limit on every single term. We will simply take the limit of each term without writing all of that down. So let's keep going. Let's find the limit as x goes to infinity. This time we're going to take the limit of the square root of 2x squared plus 1 over 3x minus 5. What is the highest power of x in the denominator? We have this x to the first power, and so we're going to divide everything by x to the first. Now we can't split this radical up and say the square root of 2x squared plus the square root of 1. We know that radicals are not linear operations. We cannot distribute them, so that's not allowed. But we are going to do a little trick. I'm going to take 2x squared plus 1. We're going to divide all of that by x. And then in the denominator, we have 3x minus 5. We're going to divide each of those by x. Now 3x over x, those cancel, and minus 5 over x. And now I want to look at this numerator. I want to come down here and simplify that, because I want to do just a little bit of trickery with that, that pink x in the denominator. And I'm going to say that x is the same thing as the square root of x squared. Now we know that the square root is the same as the 1/2 power. So the square root of x squared is x squared to the 1/2. And when we raise something with a power to another power, of course we multiply those exponents. 2 times 1/2 is x to the first, which is exactly what we have here. But what this allows us to do is sort of push that x squared up into the radical, that we can combine the radical in the numerator with the radical in the denominator to get 2x squared plus 1 all over x squared, all under the radical. That's 2x squared over x squared plus 1 over x squared, and we can cancel those x squareds. So we've simplified our numerator to just give us the square root of 2 plus 1 over x squared. Now, apply our limit, apply our little fact that we had earlier, that the limit of 1 over x to any positive power the limit at infinity is 0. And so this term is going to go to 0 when we take the limit. And of course, this term is going to go to 0 when we take the limit. But what's left over? Well, we still have the square root of 2 in the numerator, and we still have that 3 in the denominator. The square root of 2 over 3. Now, know this sort of trick of rewriting, x as the square root of x squared, and then combining the numerator and denominator of our radicals together. It may seem like a little bit of playing loose with the rules, but this is allowed, particularly when we are working with positive values of x. We can take advantage of a lot of exponent kinds of trickery. When we get to limits at negative infinity, we are going to have to be a little bit more careful about that than we do with these positive limits. So we're going to have to be a little bit more careful when we do the limit at negative infinity. So let's do that. The square root of 2x squared plus 1 over 3x minus 5. Now we're going to divide, just like we did earlier, by that highest power of x. Going to give us something like that. Divide this guy by x, and each of those by x. This is a negative limit. Limit as x goes to negative infinity. We're still going to get 3 minus 5 over x in the denominator. But now when we go to simplify the numerator, we have to be a little bit careful. The square root of x squared, I sort of justified earlier, was x, when in reality, it's the absolute value of x. If we think about this in terms of just a couple of numerical examples, if I say the square root of negative 5 squared, well, negative 5 squared is 25, and if I ask you what is the square root of 25, you're going to tell me 5. If I had never written that part down at all, and I just had the square root of 25 and asked you what that was, every last one of you is going to tell me 5. Likewise, the square root of negative 9 squared, negative 9 times negative 9 is 81, and the square root of 81 is 9. If we want to preserve the fact that our x was originally negative, we're going to need to include that when we rewrite x as a radical. So we're going to need to pick up a negative sign here and say this is negative square root of x squared. Now we can combine these radicals together. We're going to get negative square root of 2x squared plus 1 over x squared, which is negative square root of 2 plus 1 over x squared. We did all of the simplification. We got through this little equal sign with the previous example. Minus 2 plus 1 over x squared. Again, this is a very subtle point. This is a very tricky little thing to deal with, but we've got to do it if we want to make sure that when we write the square root of x squared, in place of x, that we are honest with what the sign was, the SIGN, of our original term. And square root of x squared loses just a little bit of that information. We need to make sure that we hold on to it. Now we can take our limit. We said earlier that the limit of 1 over x squared always going to be 0. The limit of 5 over x always going to be 0. That's our little fact. And now we are left with negative square root of 2 over 3. So we got two different limits at positive infinity versus negative infinity for this one. For the problems that don't deal with radicals, this is not going to be as much of an issue. For problems that deal maybe with cube roots, this is not as much of an issue because the cube root of a negative number is still negative. And we don't have to worry about that sign information getting lost the way we have to with these even roots. We take the even root of an even power. We're always, if we don't know what the sign of x is, we're going to pick up a little absolute value. And we want to make sure that once we've lost that negative sign, because we want x to be negative, we want to make sure that we hold on to it by including it in our simplification. Again, it's a little bit of a tricky thing, but just sort of kind of the most typical case is rewriting square root x as the square root of x squared, where we could potentially lose a little bit of sign information. All right. So that's going to finish up just a real quick tour through infinite limits. We're going to do the next video. I'll do a couple of more examples of those. All of the ones so far have been things like radical functions, rational functions, but there are other types of asymptotic behavior that we want to be able to talk about, and we want to be able to use some more algebraic techniques to help us with the simplification. So we'll talk about some rationalization. We'll talk about maybe some examples that involve some trig functions, and then maybe some infinite differences. So we'll do all of that stuff in the next video. Thank you.